So my PhD thesis was on gradient-free aeroacoustic shape optimization using high-order large-Eddy simulation. So first, let's go over the motivation of my study. So as we all know, aviation noise has been shown to cause a range of health problems. Here in this picture, we have the map of Montreal and the Montreal's International Airport. Those numbers are the noise exposure forecast values. And whenever this value is above 25, it means that some level of annoyance is experienced, which we can say that it covers a huge area of Montreal. So there are so many residents that are annoyed by the aviation noise in Montreal. And in addition to this figure, we have some regulations in Montreal's airport that flights are not permitted between midnight to 7 a.m. only because of the noise from aviation. That's almost a third of the day when planes can't take off and land. And if you think it over a whole year, it will be equivalent to a 3.5 month, 1/3 of a year, that we don't have any flights only because of the aviation noise. Here in this figure on the y-axis, we have the number of air passengers in billions, and we can see that historically the aviation demand is increasing. We only saw a setback during the COVID-19 pandemic, but the aviation demand has rebounded to pre-pandemic levels. And here in this graph, we show how noise regulations have changed since the 1960s. These are the exact date of each new regulation that we have. And we can see that aviation noise decreased a lot from 1960 to 1980 due to the invent of high bypass jet engines, followed by small improvements afterwards, which highlights the need for better noise reduction technologies. But first, we need to identify the noise sources of a modern aircraft. The dominant noise is the jet noise. But as I said, with the advancements in jet design, especially introduction of high bypass ratio turbofans, a significant noise reduction is achieved. But this increases the airframe noise contribution to the whole aviation noise. So further reduction in aircraft noise can only be achieved by addressing both airframe and engine noise. But how can we do this noise minimization? We need to have an aeroacoustic shape optimization framework. And in general, an acoustic shape optimization framework starts with the baseline design. We have our design, we studied aerodynamically where we need a Ffowcs solver. Then we can compute the sound using an acoustic solver. And then we can define an objective function. Let's say that we want to decrease the noise of an airfoil while maintaining its aerodynamic performance. So we need outputs from both Ffowcs solver and acoustic solver to compute or evaluate the objective function. Then that value of the objective function and our design and everything can go through an optimization algorithm, and the output of the optimization algorithm will be a new design. So optimization algorithm can give us some candidate designs. So again, we need to analyze those candidate designs to see if they have a better performance. So by using different components for Ffowcs solver and acoustic solver and also the optimization algorithm, we can have different frameworks for aeroacoustic shape optimization. So the success of an acoustic shape optimization framework largely depends on the combination of techniques employed for each of its components. So let's talk about each one of these components, the Ffowcs solver, acoustic solver, and the optimization algorithm. I'm gonna go over each one of them very briefly. And if you're interested in more details, you can have a look at my thesis or the papers that I published from this work. Or if you have any specific question, you can comment here or message me on LinkedIn. So let's start with the Ffowcs solver. There are different approaches for the aerodynamic analysis in an optimization framework, and the main two ones are the X-foil and CFD simulation. X-foil is a panel method that simulates inviscid compressible flow over airfoils. It's widely used for preliminary design because it's very simple and the computational cost is very low. You can analyze an airfoil in just seconds. but it's not very reliable for viscous flows. And whenever we have boundary layer and wake flows like separations, postal analysis, it's not very accurate for these type of analysis. But it's still a powerful tool that can be used as an aerodynamic analysis for aeroacoustic shape optimization framework. There are so many studies that they used X-foil. But how can we compute sound using X-foil? How it works is that from X-foil we get the boundary layer parameters, and those boundary layer parameters can be used as input to empirical models to get, for example, the wall pressure spectra. And we can use that wall pressure spectra as inputs to the Amyot's theory and then compute the far-field noise. There are so many different papers on these methods. So as I said, X-foil doesn't resolve this sound. And if we need more accurate simulations and more accurate results, we need to use CFD simulations. And there are different components in the CFD simulations as well. But in this video, I'm going to go over only the turbulence modeling and the spatial discretization that we can have. So for the turbulence modeling, they are usually using three different turbulence modeling. One is the unsteady RAS, URAS, which resolves the low frequency. Then we can have LES, large Eddy simulation, which resolves the broadband noise up to the cutoff scale. And also we have the DNS, direct numerical simulation, that resolves all the broadband noise. So URAS models cannot adequately capture the unsteady nature of the flow phenomena, and its usefulness in aeroacoustic optimization is a bit limited. It's still very powerful and a lot of people use it. In our study we used large Eddy simulation, which is more accurate than URAS and less computationally expensive than DNS. So now let's talk about the other component of the CFD simulations, which is the spatial discretization. So when we're dealing with fluid flows, we often encounter irregularly shaped elements, and we map each of these irregular elements into a reference element. And this technique allows us to work with familiar shapes, which simplifies the mathematical equations we need to solve. And here I'm going to compare the commonly used finite volume method, which is widely used in industry, with the Flux reconstruction approach. So let's say that we have an airfoil that we want to study it, and this is the mesh around the airfoil. As you can see, both of these figures on the left and right for finite volume method and the FR approach, both of them has the same number of degrees of freedom, which is the same number of solution points. But in the FR approach, we have coarser elements. As you know, in the finite volume method, we approximate the Navier-Stokes equation at the center of each element. But in the Flux reconstruction, we can have a denser distribution of points within each element. So the key point here is that with the same number of degrees of freedom, in the Flux reconstruction, we can have coarser elements. And also, when we want to go to higher orders, in the finite volume method, we need information from more neighboring elements. But in the FR approach, we can just simply add more points to each element. But why do we want to go to higher orders? Here on the y-axis, we have the error, and the x-axis, we have the computational cost. In red, we have the accepted level of accuracy, or it's better to say the accepted error level for RAND simulation. And in pink, we have the accepted error level for acoustic wave propagation. And we see that for acoustic analysis, we need more accurate results. So since we have lower error level for acoustic wave propagation, we need more accurate simulations. So we can see that for lower order methods, we can go to higher accuracy or lower errors, and the cost increases linearly. However, in the higher order methods, the change in the computational cost is a bit different. The behavior is different. So if we want to do RANs, it's better to use lower order methods. But if we want to do acoustic, since we need more accurate results, we can see that from this plot, higher order methods has lower computational cost than lower order methods. Before explaining why as we go to higher order methods, the computational cost increases at a lower speed, I need to explain the modern hardware architectures. So in this plot, we're comparing the number of floating point operations per second with the memory bandwidth. In the y-axis, we have the memory bandwidth in megabyte per second and the peak operation in megaflops. So the number of flops is a measure of how fast the CPU does the computation, and the memory bandwidth is a measure of how fast CPU reads data from RAM. And we can see from this plot that the historical perspective highlights a significant paradigm shift in computational architecture. So historically, we can see that reading and writing information on and off the chip was relatively fast compared to the computational power of CPUs. Back in the 1990s, when the finite volume method was developed, reading data from RAM was very quick. So no one cared if we needed to access RAM too often, which is the case in finite volume method. But nowadays, the limiting factor has changed. Transferring data on and off the chips takes longer compared to the computational speed of modern CPUs. So if many indirect operations are required, the performance will be limited by bandwidth. What does it mean? It means that if a new super fast CPU is designed, it doesn't really matter, because our application is limited by bandwidth and it's not actually any faster. This is the case with the finite volume method, and not so with the FR approach. Research shows that the finite volume method can only achieve 3% of the theoretical peak performance. However, the FR approach is capable of achieving over 50%. Okay, now let's explain why, as we go to higher orders, the increase in the computational cost is not huge. And as we said, the Flux reconstruction approach is more suitable for modern hardware architecture. But how? Here on the left, we have the percentage of runtime versus the solution polynomial degree in the FR approach, which determines the order of accuracy or how accurate our simulation is. The higher the polynomial degree, the higher the order of accuracy. And in general, there are three types of operations in the FR approach or any other spatial discretization techniques. First is the pointwise indirect access, which requires information from two or more different points, often not located beside each other, like computing common fluxes. Then we have the pointwise direct operations, which are performed point by point, and they use information from that point only, like computing the flux from solution points. And finally, we have element-wise operations, which are performed on all solution points in all elements at once using matrix multiply. So we can see that as we go to higher order, we are eventually dominated by the stuff inside the element instead of indirect stuff between elements. It means that by going to higher orders, will be dominated by element-wise operations in the flux reconstruction approach, which is the exact opposite of the finite volume, where higher orders will be dominated by indirect operations, because we need information from the neighboring elements in the finite volume method. So this is the reason why we're interested in higher order methods for aeroacoustic analysis. So far I only talked about the flow solver, but what about the acoustic solver? In general, for aeroacoustic analysis, we have two different approaches, the direct approach and the hybrid approach. For the first half of my thesis, I used the direct approach, and for the second half, I used the hybrid approach. But what's the difference between these two? In the direct approach, we compute the sound directly from the flow solver, so we don't need any acoustic solver. But how do we calculate this sound? We just take the pressure, we subtract the time average pressure from instantaneous pressure, and that's the acoustic pressure. And from there, we can compute the overall sound pressure level. But what's the problem with the direct approach? Let's say that we're interested in computing the noise 2 chords below the trailing edge. So this will be in our computational grid, and there shouldn't be any problem. But what if we're interested in a location, in an observer that is located 100 chords below the trailing edge? That means that we have to have a huge computational domain in our CFD simulation that contains that observer point. So the direct approach is really good for near field analysis, but not for the far field, because the computational cost will increase significantly. That's where we need to use the hybrid approach. So in the hybrid approach, we have both flow solver and acoustic solver. But how do we relate these two to each other? What we do is that we define a data surface that can be either on top of our airfoil or any object that we have, and we call that solid data surface, or it can contain some of the flow, which we will call it permeable data surface. And then we gather the flow field data using the flow solver on this data surface. So we compute the velocity field, the pressure field, and the density field on this data surface. And we use this as input to the acoustic solver. So in the acoustic solver, we only have the flow field on the data surface. And what it does, it propagates the acoustic wave to the far field. And the computational cost of the acoustic solver is much less than the flow solver. Okay, now let's move on to the optimization algorithms that we have. In general, there are two different techniques for optimization: gradient-based and gradient-free. Gradient-based techniques are widely used in aerodynamic shape optimization, especially with RANS simulations. This technique is great, there are so many research on it, and it perfectly works for aerodynamic optimization. But for aeroacoustic shape optimization, we have some challenges here, because the gradient-based algorithm and the adjoint equation usually diverges for chaotic problems and are best for smooth objective functions. So a more reliable and robust alternative for non-smooth objective functions and in general nonlinear dynamical systems are the gradient-free technique. And well, the gradient-free algorithms require numerous CFD simulations depending on the number of design variables. And in this study, we use the gradient-free mesh adaptive direct search algorithm as our optimization algorithm. At each optimization iteration, the MADS algorithm will identify some candidate designs. And for each one of these candidate designs, we have to run CFD simulations to compute the objective function. So let's say that we have n design variables. At each optimization iteration, we need to perform 2n CFD simulations. So the computational cost and runtime is huge compared to gradient-based techniques that we usually run a couple of CFD simulations. So let's visualize the aeroacoustic shape optimization. So we have our baseline design, as I showed earlier. Then we have a flow solver, an acoustic solver, and we evaluate the objective function, and we have an optimization algorithm. So this is when we are using a hybrid approach, because we have an acoustic solver here. And as I said, for the first half of my thesis, I'm using the direct approach, and it means that there is no acoustic solver there, because we're computing the acoustic field directly from the flow solver. So in that case, we have our design, the flow solver, objective function evaluation, and optimization algorithm. If I want to visualize it in more details, this is how it looks. So in here, we have the baseline design. Then we generate the mesh, we run our CFD simulations. In here, HORUS is our in-house solver, high order unstructured solver. And then we have some post-processing scripts to compute the objective function. And after computing the objective function for the baseline design, we have different inputs to the MADS algorithm. For example, we have the design constraints, we have the baseline design. And here delta 0 is the mesh size parameter, the initial mesh size parameter, which is a parameter that we use in the MADS algorithm. So when we give these to the MADS algorithm, it will identify different candidate designs. And as I said, for each one of these candidate designs, we need to generate the mesh, run the CFD simulations, do the post-processing, and evaluate the objective function. And after one optimization iteration, we will have the objective function value for each one of these candidate designs. And from all of these objective function values, we need to choose the best one and compare it to the incumbent design. And depending on whether we found a better design than the incumbent one, the mesh size parameter is updated. This is an iterative process, and whenever the termination criteria are met, the math algorithm is converged. We evaluated this proposed optimization algorithm on 3 different problems. First, we studied the open cavity, which is a simplified case of the panel gaps. And we have one objective function, which was the height of the trailing edge wall. And we saw that by decreasing this height, the noise was reduced by 13 decibel. And in below we have the power spectral density of the sound partial level at different Struhal numbers. And we can see that the SPL was reduced across all frequency ranges. And here we have some animations. Here we have the Q criterion colored by velocity magnitude along with the acoustic field. And we can see that the vortices are shed from the leading edge, and when they hit the trailing edge, the noise is emitted. And in the optimum case, we can see that the height of the trailing edge wall has decreased. And in that case, we have less of a negative pressure and less sound is generated. The next case that we ran is the tandem cylinder with a simplified version of the landing gears. And here we had 2 different design parameters. One was the spacing between the cylinders, which we can think of the spacing between the landing gears, and also the ratio between their sizes, the diameters. And in the optimum case, we had the downstream landing gear to be bigger and also closer to the upstream one, which resulted in almost 11 decibel noise reduction. And here again we have the Ph.D. of SPL. But this is a bit interesting that in the optimum design we have higher intensity of Ph.D. over a broad frequency range, but we got lower sound partial level value. As you can see here, for the optimum case, the Ph.D. is higher, the intensity is higher for a wide range of frequencies, but the value of sound partial level is lower. This can be attributed to the baseline design producing high intensity sound at specific frequencies, these 3 peaks that you can see, and all of these peaks are reduced. And also the optimum design distributes its energy across a wider frequency spectrum. And here again we have the Q criterion colored by the velocity magnitude and the acoustic field. And we can see that flow separates from the upstream cylinder, and then the vortices hit the downstream cylinder, which creates noise. But in the optimized one, the separation of the upstream cylinder is gone, which resulted in noise reduction. And finally, the third simulation that we had for the direct acoustic analogy was the NACA W12 airfoil at an angle of attack of 6 degrees. So here the airfoil is at a low Reynolds number, and we can think of it as sections of propeller's blade. Here we have 4 different design parameters that are there to generate a new NACA 4-digit airfoil. And this is the objective function that we define here, which is the overall sound partial level at an observer location. And also we have penalty terms here for aerodynamic performance. One, we have the lift coefficient that we want to maintain it, and for the drag coefficient we want to reduce it if it goes higher to the baseline design. And if it's lower than the baseline design, it's fine, we just leave it to make it lower. And here in red we have the optimum design, which we can see that the new airfoil, the optimum airfoil, is a bit thinner, and the noise is reduced by 5 decibel, while the time average drag coefficient is decreased by 7.4%, and the lift is also increased by 2.4%, which We didn't want to increase the lift, but it increased. And here we can see the Ph.D of SPL across different frequency ranges and the animation of the same thing, the Q criterion colored by velocity magnitude. And here we can see clearly the separation point and the vortices that pass the trailing edge, which results in noise emission. And in the optimum case, we can see that we have earlier separation, which means that we have less energetic eddies when it separates, and we have lower noise. Okay, so these were for the aeroacoustic shape optimization for near field, where we didn't have any acoustic solver. But for the far field, we have an acoustic solver, and we're using an acoustic analogy, which is Ffowcs Williams and Hawkings formulation. Ffowcs Williams and Hawkings formulation is just the exact rearrangement of the equations of mass and momentum conservation. We have three different components, the monopole, dipole, and quadrupole, and there are different solutions to these equations. The one that we were interested in was the integral solution to the Ffowcs Williams and Hawkings equations for wind tunnel problem. And also we used a permeable data surface, not a solid one. And if we use a permeable data surface, and our data surface is large enough to contain all the noise sources, then we can neglect the quadrupole term in the pressure. So the first two terms are the thickness and loading pressure terms, which are just simple surface integration. But the last term is a volume integration, which is computationally very expensive. So we can neglect that term if we include all the nonlinear flow field and the noise sources within the data surface that we choose. And after implementing our acoustic solver, we need to validate it. There are different analytical test cases that we verified and validated our acoustic solver with, and all are explained in the thesis. But in here, I'm gonna just explain the validation of the acoustic solver with the CFD simulation. So we ran the NACA W12 airfoil, and the observer was located 2 chords below the trailing edge. So we first used the direct approach, meaning that we ran the CFD simulation on this airfoil and compute the sound at 2 chords below the trailing edge in the near field observer. And we also used our acoustic solver. And here we have the data surface that we used in the CFD simulation. And we gathered the flow field data on this data surface and used it as input to the Ffowcs Williams and Hawkings solver. And we used it as input to the acoustic solver. Here the data surface is open-ended to prevent erroneous acoustic wave generation, which are associated with the vortices that are crossing the surface. And after obtaining the sound pressure level at the near field observer using the acoustic solver, we saw discrepancy between the results from the acoustic solver and the direct approach. And the reason was the periodicity in the spanwise direction. So what we had to do was to duplicate the data surface in the spanwise direction. And by duplicating it large enough, we could get to the direct approach. So again, we did the far field aeroacoustic shape optimization using NACA 4-digit airfoil, and the observer now is located 10 chords below the trailing edge. And we have the same objective function. So here we didn't know how many duplication we need. So what we did was that we used different data surface duplication in the spanwise direction and then compare the results to see when it converges. Here on the left, we have the time hysteria of pressure perturbation. And we can see that by duplicating the data surface in the spanwise direction to 25 chords, we converged. And here are the exact values of sound pressure level using different duplication length. And we can see that from 17 chord duplication to 25 chord, the SPL is almost converged. So the aeroacoustic shape optimization framework is a bit different here because we have the acoustic solver now. We called the acoustic solver Pi FWH because it's the Ffowcs Williams and Hawkings formulation implemented in Python. And here everything is similar to the previous one, but the only difference is that now we don't run safety simulations one after the other. And what we do is that within each optimization iteration, we perform all the simulations simultaneously. So HORUS is run in parallel using 4 GPU, and also each candidate design is run in parallel. So we have 2 layers of parallelism here. So as I said, this is all automated aeroacoustic shape optimization framework, and whenever a new candidate design is identified, generating the mesh takes around 10 minutes, and running HORUS on 4 GPUs on supercomputers takes about 12 hours, and the Acoustic Solver Ffwh is run on CPU, which takes around 20 minutes, where we're duplicating the data surface, which is a 300 gigabyte of file. And the post-processing and the maths algorithm takes just seconds to run. So here we had 4 design variables. So it means that at each optimization iteration, we will have 8 different candidate designs. So we need to perform 8 different safety simulations at each optimization iteration. And as I said, each CFD run takes 12 hours, which is half a day. So 8 CFD simulations will be 4 days for each optimization iteration when you're using the serial implementation. And this problem converged after 26 maths iteration. So 26 times 8 is 208 safety simulations required for this optimization problem. And as I said, each safety simulation takes 12 hours or half a day, meaning that this optimization problem, if we wanted to run it in serial, would have taken 104 days to complete, which is 3.5 months. But with the parallel implementation, we run all of these simulations at the same time within each iteration. So when we have 8 CFD simulations per iteration, all of them are run in parallel, so each optimization iteration takes half a day, no matter how many candidate designs we have and how many CFD simulations we need to run. So the runtime decreases drastically, and just imagine if we have more design variables. Let's say that we have 10 design parameters or 100 design parameters. If we want to run it in serial, it will take years. But if you're doing parallel implementation, the runtime will be much lower. So the result of this optimization problem is that the noise is reduced by around 15 decibel, which is huge, and the time average drag coefficient is decreased by 14%, and the lift coefficient, which we wanted it to be the same, increased by only 1%, which we get a really good results here. So the contribution of this work, in a summary, was that we developed a far-field aeroacoustic shape optimization framework using high-order LES. We also developed a parallel GPU-based shape optimization framework, which is suitable for many core hardware architectures, and also it eliminates maths runtime dependency to the number of design parameters. We obtained significant noise reduction for a range of engineering applications, and also we demonstrated a promising technology that enables the design of next generation aircraft. And I want to thank Concordia University and Digital Research Alliance of Canada for providing resources for this study. And again, Concordia University, NSERC, and FRQNT for providing the funds of this study.